So we're moving now from what we've just seen, basically data preparation, data providing from OpenStreetMap to a data consumer, which is me. And I'm introducing you now to what we call the global dynamic exposure model or platform exposure in the sense of what buildings are exposed to natural hazards. So to motivate this a little bit, let's look at the Vesuvius area. This is the, let's see it, sorry. There's the volcano, there's Naples, and here is the shake map, the intensity of an earthquake that occurred under the volcano in 1999, and you see strong shaking around the edifice of the volcano and then weaker around it. Here's the historic lava flow. This is the flood hazard for this area, and here are the buildings. And what you immediately can see is how the buildings are differently affected based on their location on the different hazards. Some buildings are affected by all the hazards, others only by a few, etc. And these are not even all the hazards that you can imagine in that area. But it's not just the location of the building, it's actually also what is in the building. How is it used? What structure it is? Here you see a little uh, zoom out of this area, and you see industrial buildings in brown that are affected by potentially the floods, while the commercial buildings in blue, for instance, are not affected by the floods. And yet even industrial buildings of different types than, let's say, the green agricultural buildings, usually greenhouses, or the red ones, which are residential, and of course, usually not as strongly built as commercial units, etc. So what we actually want to know to assess the risk to natural hazards globally is every building, the exact location and the size, its type, so the structural type, its vulnerability to the different hazards, the number of people that are expected to be in the building, and of course, when you go into economic losses, also the value of these buildings. The issue is, of course, that the building stock is not something completely static. We actually have a very dynamic system. One of the main reasons, of course, is urbanization. So we have cities that are growing very quickly, like Tehran, doubled in size in the past 20 years. Then we have modernization. So buildings are taken down and replaced. And a good example for this is Japan, where buildings usually, on average, after 30 years are taken down and being replaced. So if you have an old building that doesn't follow the earthquake building code, within a couple of years, you may actually have a new building there that does follow the earthquake code, and therefore will be much safer to live in. And then there is the time dependence, which means we have consecutive hazards to occur. We have main shocks, earthquakes, and aftershocks. We have earthquakes and tsunamis, earthquakes and landslides, and so on. And so the first hazard, the first catastrophe may actually weaken the building structure, create some damage, and then the building is way more vulnerable when it comes to the second one. So the challenge that we were facing was actually to create a model that is high resolution on the global level. So we actually want to describe every building separately globally to have a better grasp on their vulnerability to different natural hazards. And we want this model to be dynamic in order to actually capture all the changes that are occurring. For obvious reasons, the classical exposure modeling strategy, which is you take an engineer, send him into the field, say, okay, you check all of these buildings, then report back what kind of structures do we have, what is the vulnerability of these buildings, etc., doesn't work here because we have quite too many buildings in the world. So what we've done is we completely changed the paradigm of this, and we go with open data and try to extract as much information as possible. And therefore, we developed a platform around the OpenStreetMap ecosystem, as this was our first data intake. This is then integrated with additional models about building types per area, let's say countries, municipalities, in which we get all the engineering information that is necessary to understand what type of buildings are actually present in such an area. And then in our rule-based engine that I will explain in a second, we are processing every building separately. We're taking all the attributes and then trying to figure out which of these engineering types does this building actually consist of and how many people live in there. So we need to have more ideas of the size, etc. And so we have basically as an input various open data sources and the exposure models, the classical exposure models that describe building types per country or region. And these rules that kind of process everything is what you could call the expert knowledge. And this is then all done in a real-time updating system for the building classification to create what we then call the dynamic exposure. The key element of this whole thing is Robotnik, our assembly line, where we actually process every building as it comes in and try to assess everything. And the key is that in this case, we get to a probabilistic estimate of all of this information that we don't have in a deterministic way available. So what I'm talking about is what is the data that we're looking at. So here's an eatery in Tokyo. And the first thing that we can deterministically estimate is, of course, the footprint size and the location. We take this from OpenStreetMap or other data sources as a geometry. Then we have often the number of stories, and then together with the footprint, we can estimate already the floor space, which is a good hint on the size of the building, population, value, etc. From OpenStreetMap, we are able very often to actually estimate what kind of occupancy this building has. So in this case, it would be sort of a retail commercial unit. And then what we do is we take all of this data that we know deterministically about the building, and then we try to figure out to which of these different building types that are present in that region it matches. So we gave probabilistic estimates of what kind of structural type this is, what is the structural value or reconstruction value of a building should it be destroyed in a natural catastrophe, about the population, which then is scaled with the size, the floor space of the building and its use. And in the future, we're working on more attributes like the building context. So in this case, for instance, is this building freestanding or is it surrounded by other buildings that touch it? What is the building structure in the neighborhood? How dense is the neighborhood, etc.? Because this can all give us hints on what type of building that might be. The footprint shape, together with the roof shape, will also help us to understand the different architectural types that we have, and then the construction year, of course, can tell us according to which codes these buildings have been built. The processing we do is OpenStreetMap is one of our main data sources and the one that is changing the fastest. So we actually take the minutely diffs from OpenStreetMaps, process all the changes, whatever has happened to a building or building has been added goes into our assembly line and is then feeding into the model within like 5 to 7 minutes, and then we have an updated version of that one. So the global dynamic exposure, what we sometimes call our open building map today, consists of 2.7 billion building data sets. And as you know, OpenStreetMap is growing. The building data in OpenStreetMap is growing by about 5+ million building footprints every month, so 2 per second in average. And I just want to stress that whenever we get this one building, we process it separately. We're not processing in bulk, say, okay, buildings in that area are this and this. No, every building is separately processed. Here's the main building data sets that we currently use. It's OpenStreetMap, Google, and Microsoft. This is the building conflation. It is done geometrically. So we have OpenStreetMap as our top source, then Google, then Microsoft. And so we first populate the world with OpenStreetMap, then we fill the gaps with Google, and then with Microsoft. The overall building completeness looks pretty good. This is not showing such high values for the simple reason that we're actually comparing a model with a model, the other model being the global human settlement layer, which is pretty imprecise, but it gives you a good hint where we're actually lacking buildings, which is in China and parts of Korea and in the Middle East too. The areas where it's sort of in the yellowish and reddish is usually pretty much complete. A bit different is the picture if you look into the occupancy types. So in Central Europe, all over Europe actually, and then parts of Africa and India, we're actually pretty good in being able to estimate the occupancy of the building because there's sufficient additional data in OpenStreetMap that gives us a hint of whether these are residential buildings or commercial, industrial, military, educational, whatever entities. But in other parts of the world, a building is sometimes just a building. We don't know how it's been used. Here's a detail of different occupancy types. In Saint-Denis, north of Paris, you can see in red all the residential types. We even distinguish a couple of different residential types here. Then educational buildings, universities, schools, etc. In blue, the commercial ones. In purple, all the sort of mixed occupancy types, etc. You don't see so much agricultural one, but there's a strong industrial complex over there. As I said, we try to understand the structural types of the buildings. Here's a distribution of different building materials. that we have assigned to these buildings. So from earth and adobe, top left, and wood, masonry, unreinforced masonry, important for earthquakes, and then to steel and metal and concrete buildings down there. And you see the distribution is quite different if you look at it on a global scale. When we come to the probabilistic estimates of the structural types, what we do is illustrated in this example here. So this is the city of Aarhus, the downtown of Aarhus in Denmark, and 88 types, different structural types are present in Aarhus according to engineering information. And so, as I said, we try to use the variables that we know from OpenStreetMap and the other sources that we pull in to understand which of these 88 types a building can belong to. And you see that we are able to reduce this in the case of the yellow buildings to like 1 or 2 different types. In the green buildings, somewhere in the order of 10. But there are, of course, some buildings like the purple ones where we're actually not able to say anything. We don't have enough constraining information to actually select some of these 88 types. Then this building is represented as an average building consisting of sort of 88 potential types. This is not only true in sort of well-regulated countries like Denmark, where we have a lot of information. Even here in Dhaka in Bangladesh, as soon as we know the height of the building, we can significantly reduce the number of different building types from 34 to a low single-digit number. We can also compute the structural value. Overall, looks pretty much like a population density map, but overall it tells you where the highest losses are to be expected should a larger catastrophe occur. Our model coverage is already global. In the case of the yellow countries like Greenland, Antarctica, and some island nations, we don't have structural information, but we collect all the other properties and also distribute the population over the different buildings that are in there. Because I'm actually a seismologist and not a building model or engineer or anything, we've also created a loss calculator so that we can actually compute the effects of earthquakes, or as we're doing now, floods too, and want to move to further hazards on this building data set. So you basically take, in the case of an earthquake, you take a ground motion field. So how strongly is the earth shaking on different locations? For the flood case, you would take a distribution of inundation depths with water, etc. And then this loss calculator is analyzing every building and its vulnerability function to that very specific hazard. And then you can aggregate your results per tile or per building, as I will show right now. Here's an example for the Turkey earthquake. On the left-hand side, you see the western part that was hit by the Turkey earthquake. And you see the distribution of fatalities per square kilometer. On the right-hand side, we compute the building damage. So for complete damage, so the probability of, no, the expected number per square kilometer of completely damaged buildings during that earthquake. We can also do other scenarios and analysis. Here's, for instance, a flood risk of industrial buildings. So you see in light blue, you can see patches where there's a high flood risk with sufficient, like I think 2 meters of flood for a 1,000 year return period expected flood. And then if we have a concentration of industrial building in one of these flood zones, we highlight this in red, and you see where you actually have these kind of flood hazards for industrial buildings. These are not all the industrial buildings. These are only the industrial buildings that are in a flood hazard zone. So we can look into a detail here in Bangkok. You will see that there is like an industrial zone here where there's this large accumulation of industrial values. And then we can even go further and go down to the building scale and see all of these buildings are on this blue patch, which means there's a significant flood hazard in this area. And then the buildings are colored by the structural value, which means by the probable loss of the industrial values in case of a flood, according to this flood hazard model. I will give you another example that highlights some weaknesses and where we're going to go from now on. So this is the Coquimbo earthquake that hit Chile in 2015. Here's the distribution of damage of the buildings within the city of Coquimbo. And then this is the tsunami that actually later hit the area. And what you can clearly see is that there's a lot of buildings that were sort of just hit by the earthquakes, but then there are also buildings that were hit by the earthquake, damaged by the earthquake potentially, and then hit by the tsunami. That is already a big win, that you can identify these buildings and how many buildings have at best been affected by the tsunami, and also that you can see if there's already been a previous damage, so that you can have a better idea of what is going to happen during the tsunami. But the big problem with tsunamis and some kinds of hazards is that this is affecting people that are not in buildings. So what we actually need to do now is to add the people to this exposure model that are not in buildings. So for instance, at this wonderful beach, should a tsunami hit, our model would just report no casualties because these people are not in the buildings that will be swept away. So we need to figure out where are the people. If they're not in the buildings, this means public places, busy streets, restaurant areas, beaches, etc. And then we also have to figure out what are the daily, weekly, and seasonal variations. And luckily, we'll have a student coming in next month to work on this, so that we understand that, for instance, touristic places, double, triple their population during the tourist season, usually summer. But we also have this daily variations, working time, non-working time, and weekly variations of work days and weekends. We're going to move further to other hazards. So this is different types of floods we want to include. Then also sort of climate change relevant hazards like heat waves, where then knowing the structural type, the strengths of the walls, how much are they actually cooling is of importance. And of course, the upcoming hurricanes and typhoons that we have to expect will hit us more heavily in the future. Recently, we're just starting to introduce 3D buildings. The EU is preparing data sets for what they want to have be 500 cities in the member states, but there's also data sets in the US and in the Japan plateau data set that we're collecting and putting in. And nicely, the data sets we currently have already go to level of detail 2.2, if not higher. So we get the surface semantics, we can figure out what is the roof type. That again helps us understanding what kind of structural type we actually see, because mostly the 3D data sets only describe the shape and don't give us any further information about the types of these buildings. We're going to include more about infrastructure, unfortunately, because we're an open data set. This will likely only include the above ground infrastructure, because we cannot see anything below the surface like power lines or water lines. And we want to put a focus on so-called engineered buildings, because for these buildings, very often vulnerability functions do not exist. People don't really know what's going to happen to them. But this will require actually an extension from the pure data modeling to actually go there and putting acceleration sensors into these buildings to see how they react to slight shaking and maybe stronger shaking. So from here on, we are trying to just update the model constantly and continue the research to improve it, to make it better and more useful. We want to increase further coverage of various attributes and add more data sets as long as they are open and can be combined. Move into AI techniques to increase the coverage, not only of properties, but also of the area, so we can capture maybe even areas where we currently don't have engineering information, and use large language models to collect this information from publications and whatever is out there. And we would like to stimulate the collaboration with engineers, communities, municipalities, and activists. They can contribute either with data, they can contribute with rules in our engine on how buildings can be interpreted, what is the information that can be kind of squeezed out of those, and also just in general, use this data set, give us feedback, give us information of what is good, what is bad, and what we can do to make it better. And with this, I stop here. Thank you very much for your attention.